Hello lovelies, in this video we're going to be going through your OCR-A A-Level Chemistry paper 1 that we've written for 2024. Now, what I want you to pay attention to are the exam skills, how we've structured the answers, how we've structured the mathsings, how we've looked at how the questions are going to be interpreted to make sure that when you go into the real exam you can take all of the knowledge and all the skills that we've shown you in this video and apply them and get great grades.
Here we're asked to calculate the relative formula mass of a lithium sulfate. And the first thing we need to do here is to work out the formula of lithium sulfate. We should know that lithium, because it's in group 1, has a 1+ charge. And we do need to know the charge of sulfate is 2-. For that reason, we need 2 lithiums for every 1 sulfate to balance out those charges. So the formula is Li2SO4. So now that we have this information, we can work out the relative formula mass of lithium sulfate. So if we have a little look in the periodic table there, we can see that each lithium has a mass of 6.9. So 6.9 times 2, plus the mass of sulfur, which is 32.1, and then plus 4 times 16. So if we tally that up into our calculator, we end up finding that the relative formula mass is 109.9 grams per mole, and that is C. So C is our answer. Here we're asked to calculate the mean titra to plus or minus 0.05 centimetres cubed from these results. So to work out a mean titra, we need to find the concordant results. Now, concordant results are the results within 0.1 centimetres cubed of each other. So in this case here, first off you need to know that we don't include the rough titra, that is just there as a ballpark figure so that we have a rough idea of where to start going slower with the dripping in. And then if we look at the results, we can see that only 2 and 3 are concordant, so within that 0.1 centimetre cubed. So we need to just find the mean of 2 and 3. And to do that we just do 13.55 plus 13.50 and we divide it by 2 because there's just 2 values. Now that gives us 13.525 centimetres cubed. However, and this is the sneaky bit in this question, we need to round it to the nearest 0.05. And so if we look at a little number line here, okay, so we've got 13.525 and on the lower end of it we've got 13.50. And on the upper end of it, we've got 13.55. That's considering that we're going up to the nearest 0.05 each time. Now, 13.525 is smack bang in the middle. And so because it's in the middle, we're going to round up. And so 13.55 is our answer to this one, the mean titra to 0.05 centimetres cubed. So the answer to this one is A. Here we're asked to identify the statement about the element barium that is false. So the way to do this is just go through them one by one and see if you can find the answer. So it starts by stating the reaction of barium with oxygen is more rapid than calcium with oxygen. So to answer this, let's remind ourselves of the periodic table. By all means glance over at the periodic table now and have a look at group 2. So we know that it goes from beryllium to magnesium, to calcium, to strontium, to barium. So barium is lower in the group and therefore it has more shells. And the fact that it has more shells means that it's going to be more reactive because it's easier for it to give up its electrons. So if it's more reactive, then yes, it will react more quickly than calcium. So the next fact states that barium hydroxide is insoluble in water. Now we should be aware that no, barium hydroxide is actually soluble in water, and therefore that is the false statement. So we don't actually need to go any further in this question. If this happened in an exam, then I would advise you just to move on to the next question and not to just check out the other bits because you found the answer. However, as we're here anyway, let's just have a chat through C and D and determine that they are in fact true. So for C, we're told that effervescence is observed in the reaction of barium with hydrochloric acid. We should remember that when we have a metal and an acid, we make a salt and hydrogen. Now that hydrogen is a gas that will bubble, and that is our effervescence. And with D, the melting point of barium is less than that of calcium. We should be familiar with the fact that generally as we go down group 2, the melting point generally decreases, with the exception of magnesium. So there we have it. That is why B is our false statement. The rest is correct. And so we can have a look at the next question. A chemist was monitoring a combustion reaction. The initial temperature was 22.3 degrees C, and it reached a maximum of 85.6 degrees C. The error in the digital thermometer reading was plus or minus 0.1 degrees C. Here we're asked to calculate the percentage uncertainty in the temperature change. So this question is about temperature change, so first things first, let's work out what that is. And to do that, we just do 85.6 minus 22.3. That ends up giving us a change in temperature equal to 63.3 degrees C. So the percentage uncertainty then is always equal to generally the uncertainty divided by the measurement times by 100. Now in this case though, we've kind of got two different uncertainties that need to be factored in. There's the uncertainty in the initial reading of temperature and in the final one. So we're going to do 2 times that uncertainty, 2 times 0.1, and then we're going to divide it by that measurement of 63.3. We then times by 100 to get it as a percentage. And doing that, I end up getting 0.315957%. And looking at the available options here, I can see if I round that to 2 decimal places, I can see C is my answer. And so that is the percentage uncertainty in the temperature change. Main thing to take away from that is whenever we have more than one measurement, which is anytime we do a temperature change, when we use burette readings, even when we use a balance to take a mass, because we always zero it first, we need to times that uncertainty by 2. Identify the overall equation for an iron 3 titration with the following reduction half equation. So if this is the reduction half equation, we need to write the oxidation half equation involving iron 3. So that's going to be Fe2 plus goes to Fe3 plus an electron. So the Fe2 plus has lost an electron and we have an oxidation equation here. So that's one of our half equations. The other half equation is the one that they gave to us. So I'm just going to write this down here and I'm going to show you what we do next. Now, whenever we want to combine 2 half equations, we need to make sure that they both have the same number of electrons. Now, the second equation has 5 electrons, but the first one with the ions only has 1. So what we need to do is multiply that first equation by 5. Now, both of these equations have 5 electrons. Now, what I like to do is to do a little line that divides the reactants with the products. And anything that's on both of them, I like to cancel down. And in this case, you can see that's just the electrons. Now what I do is I take all of those reactants, so the 5 Fe2+, the MnO4- and the 8H+, and I combine those together to make my reactants of my overall equation. I then take all of the things on the other side of my little line, and I combine those together to make my products. So my products will be 5 Fe3+, Mn2+, and 4 H2Os. Now, looking at the options here, that could then be either B or C. But the difference is the state of those ions. And because they are ions of iron, they will be aqueous. So for that reason, we're going to choose B. It cannot be C because that says that we have solid ions there, and we can't have those. We can also eliminate D and A because their overall equations have different numbers of atoms in them, so it just doesn't balance out. So that leaves us with B for our equation. That's our overall equation for this titration. Here we're asked to identify the shape of this complex ion. So what we need to do here is to look at the ligand that we have. So this NH2CH2CH2NH2 is known as ethane 1,2-diamine. And that's a very important ligand that we need to know about. And the reason why this is such an important ligand is because it is a bidentate ligand. The two nitrogens on those two amine groups each have lone pairs that they can donate to form a coordinate bond. And because they're each bidentate, we have those two coordinate bonds. So the fact that we have 3 of these ligands means that we're going to have 3 times 2, 6 coordinate bonds in total. We should recognise that whenever we have 6 coordinate bonds, we have an octahedral shaped molecule. So in this case, D is our answer. So we're going to write down D in our answer box. Identify the letter of the process or reaction that would have the greatest increase in entropy. Now, if we're increasing the entropy, that means that we're getting more disorder in our system. Now, that could mean we've got more moles of stuff, or it could mean we're changing from a solid to a gas or something similar. So let's run through these one at a time and work out which one has the greatest increase in entropy. Well, straight away I can eliminate the freezing of water. The reason for this is we go from liquid water to solid, so there's less disorder. So definitely not increasing in entropy. So now let's look at the equation for the neutralisation of aqueous sodium hydroxide with aqueous hydrochloric acid. So we know that when we have a base and an acid, we end up making a salt and water. The salt will also be aqueous and the water is a liquid. We should know that the aqueous substances, so all the sodium hydroxide, HCl and the NaCl, have slightly more entropy than the liquid water. As a result of this, we can see that as we're going from just aqueous to aqueous and water, actually we're going to see a slight decrease in entropy here as well. So B sees a decrease in entropy, not the increase that we're looking for. So we can eliminate B as well. So next up, we can have a look at C, the formation of water from its elements. So let's write down the equation for the formation of water from its elements. So of course we know water is made and water is a liquid, and we're forming it from H2, which is a gas, and half an O2, which is also a gas. So here we're going from gas moles to liquid moles, which means again we've decreased the amount of entropy we have. So delta S is also negative here as well. So for that reason, without even thinking about D, we know D is the answer. But let's look at why that sees an increase in entropy. So we've just got 1 mole, we've just got the calcium carbonate, and that is a solid. And then we form 2 things. We form calcium oxide, which is also a solid, and carbon dioxide gas. Now that gas is going to have far more entropy than the solids. As a result, our entropy change is positive. So D is definitely our answer here. 4.45 grams of potassium hydroxide was dissolved in 0.5 decimeters cubed of water. Here we're asked to calculate the pH of the solution. So in order to answer this, we need to first recognise that potassium hydroxide is an alkali. And when we want to work out the pH of an alkali, we have 2 steps. The first step is to use the equation Kw equals the concentration of H plus times by the concentration of OH minus to work out the concentration of H plus. And then we can put it into our standard pH equation that states that pH equals minus log H plus. So we've got quite a few steps to do in this multiple choice to get to this point. First thing we're going to need to do is to work out the concentration of the OH minus ions. To do this, we're going to have to first work out what the MR is of potassium hydroxide. By doing this, we can look at the periodic table, see that potassium is 39.1 and then add 16 and add 1. That ends up giving us an MR of 56.1. So now we know the MR of potassium hydroxide. The reason why that's helpful is we can now work out the number of moles of potassium hydroxide. That's mass over mR, so that's 4.45 divided by 56.1. So that ends up giving us an answer which is equal to 0.0793. So that's the number of moles of potassium hydroxide. However, we need the moles of hydroxide. You need to remember that when potassium hydroxide dissociates, it dissociates to K plus and OH minus. Here you can see we have a 1-to-1 ratio between the potassium hydroxide and the hydroxide ions. So therefore, the number of moles of the hydroxide ions is just the same. It's still just 0.0793. So now we know the moles of it, we can work out the concentration. Now, because the unit of volume here is decimeter cubed, consistent with moles per decimeter cubed of concentration, we can just find the concentration by doing moles over volume. So that's 0.0793 divided by 0.5. And so there, the concentration of the OH minus ion is 0.1586 moles per decimeter cubed. So using our Kw equation now, if we rearrange this to get H plus as the subject, we can see that the concentration of H plus is going to be equal to Kw over the concentration of OH minus. Now Kw is given in our datasheet. Kw is equal to 1 times 10 to the minus 14, and we're going to divide that by 0.1586. So popping that into the calculator, I end up finding that the concentration of H plus is equal to 6.3 times 10 to the minus 14. So now we know this, we're on to the final step. We can say that the pH is going to be equal to minus log H plus. So pH in this case is minus log of 6.3 times 10 to the minus 14. Now that gives me 13.2, which is my answer. So I'm going to write that down and then move on to the next question. The first order reaction began with 20 grams of a sample. After 10 minutes, there was 5 grams remaining. Calculate the rate constant for this reaction. So the method that we're going to need to use for this is the equation that states that K, the rate constant, is equal to ln2 over the half-life. We have enough information here to work out what that half-life is, okay? We know that it takes 10 minutes to go from 20 grams to 5 grams. Now, in going from 20 grams to 5 grams, we can imagine that we've halved the mass twice. First off, we went from 20 down to 10 grams, and then we went from 10 to 5 grams by halving each time, okay? So if it took 10 minutes to go all the way from 20 to 5, we can see it must have taken 5 minutes to halve and then another 5 minutes to halve again. So we can say then that the half-life is equal to 5 minutes. However, remember, we don't like to use minutes, do we? Particularly looking at these units, they're all in s to the minus 1. So we need to convert 5 minutes to seconds. So here we've got 5 times 60, because there's 60 seconds in a minute. So that's 300 seconds. Therefore, we get K by doing ln2 divided by 300. And that gives me 2.31 times 10 to the minus 3, which is A. Here we're asked to identify the group 6 hydride with the greatest boiling point. Now, out of all of these, only one of these has hydrogen bonding. Hydrogen bonding is found where there's relationships between H and O, H and F, and H and N. So this is the only bond that is going to experience hydrogen bonding between the different molecules. So for that reason, and the fact that hydrogen bonding is relatively speaking strong in terms of intermolecular forces, H2O is going to have the highest boiling point out of these 4. So that is our answer. Identify the letter in the table that represents the bonding in ammonia, NH3. So what I would do here, if I didn't know this by memory, is I would draw the dot and cross diagram. I know nitrogen has 5 electrons in its outer shell, as it's in group 5. Hydrogen has just 1. And so the bonding looks like this. I can clearly see that I have 3 bonded pairs of electrons and 1 lone pair. So comparing it to the table, 3 bonded pairs, that narrows me down to B or C, and 1 lone pair, which straight away tells me my answer has to be B. So B is my answer. And we should know as well that ammonia has a bond angle of 107. And we should know that any combination of 3 bonded pairs and 1 lone pair of electrons is going to give us a bond angle of 107 degrees. The Boltzmann distribution graph shows the results of an experiment 1. A parameter was changed in experiment 2 and it produced the Boltzmann curve shown by the dotted line. I'm going to colour this one in pink just so it's really obvious to us. Here we're asked to identify the statement that's true. And we're told some facts about temperature or catalyst. First things first, I want to remind you that when it's a catalyst, what happens is the activation energy gets lowered. The shape of the curve doesn't actually change. So we can eliminate C and D. However, we should know that as we increase the temperature, we're going to have more particles that have a higher energy. And therefore the shape of the curve will indeed get broader and flatter. So the result of that is the answer is B. The temperature must have been increased in experiment 2. The following reaction reached equilibrium. Here we're asked to identify the statement which would favour the largest yield of the product. So here let's have a think about how temperature and pressure is going to affect this. Here I can see I have got an exothermic reaction, and I can see that because the enthalpy change is negative. So if it's exothermic, that means the forward reaction of this reversible reaction is exothermic, and the backward reaction would be endothermic. So we need to ask ourselves, to get the largest yield of the product, what is going to make it favour the exothermic direction? So because equilibrium and Le Chatelier's principle says it always wants to get things back to how they were, we can imagine that decreasing the temperature would lead to the equilibrium favouring the exothermic direction, because it's going to want to increase the temperature back. So decreasing the temperature is what we need. So for that reason, we can eliminate A and C that suggest increasing the temperature would increase the yield. Now let's think about pressure. Because we have gases here, pressure is what we want to consider. So we can see we've got 2 gas moles on the reactant side and 1 gas mole on the product side. Again, equilibrium will always shift to minimise change. So if we wanted it to shift towards the product side again, we want to increase the pressure. So here we know that the answer is going to be D, because decreasing the temperature and increasing the pressure is what we need to do to get that largest yield of product. An investigation into the energy released in the 1-minute combustion of propanol was conducted. The student was then advised by their teacher to repeat the experiment, but this time to use a draft excluder. Identify the statement that's false for the second experiment. So to answer this, let's think about why we're using a draft excluder. A draft excluder is going to minimise the movement of air, and therefore that should minimise the heat loss to the surroundings. More of the energy should be able to stay contained and heat up the water. And therefore this energy change should be able to increase. And as a knock-on effect of that, the change in the temperature would increase too. And that's because less heat is getting transferred to the surroundings, more will heat the water. So now let's think about this next point. The specific heat capacity would stay constant. Well, specific heat capacity is a property of a material. External factors, like draft excluders, won't affect it. In this case, if we're using water as the thing we're going to heat up, the specific heat capacity would be the property of the water or of whatever material we're heating up, and that does stay constant. So that leaves us with the mass of propanol used would increase. That's the only one left here, so C is going to be our answer. That is the false statement for this second experiment. 2 grams of magnesium hydroxide was added to 200 centimetres cubed of 1.5 moles per decimetre cubed of nitric acid. Here we need to calculate the concentration of the nitric acid after the reaction had gone to completion. So let's have a little look at this then. It's going to be quite a tricky one. First thing we need to do is to write a balanced equation, and then we can work out how many moles are left over after this reaction finishes. So we've got magnesium hydroxide here. The formula of this is MgOH2, and that's because magnesium is in group 2, so it's got a 2+ charge, and hydroxide is OH-. So now that we've got the formula for magnesium hydroxide, and hopefully we know that the formula for nitric acid is HNO3, we can get to work in writing our balanced equation. We know that hydroxide plus an acid makes a salt plus water. The salt in this case is going to be magnesium nitrate. And because the nitrate ion is just -1, the formula is MgNO3 So now I need to balance this. I can see in magnesium nitrate I've got 2 nitrates, so I need 2 nitric acids. And as a knock-on effect of that, I now need 2 waters as well. Now we've got this balanced equation here. Let's work out how many moles we have of magnesium hydroxide and then how many moles of nitric acid. Let's get started with the moles of magnesium hydroxide. Because we're given the mass, we need the MR of magnesium hydroxide. So that's going to be 24.3 for the magnesium, plus 2 times 16 for the oxygen, plus 2 times 1, and that gives us 58.3. So now we know that, we can work out the moles of magnesium hydroxide. That's going to be equal to the mass over the MR, so that's 2 over 58.3, which gives us 0.0343 if I round that there. Now let's look at the nitric acid. We know the concentration is 1.5 moles per decimetre cubed, and we also know that the volume is 200 centimetres cubed. So because we've got centimetre cubed and moles per decimetre cubed, I'm going to say that moles is concentration times volume over 1000. And that gives me 0.3 moles of nitric acid. So we've got a lot more nitric acid there than we have magnesium hydroxide. In this case, the nitric acid is in excess. We must remember though that we've got a 1:2 ratio. So because the nitric acid is in excess, all of the magnesium hydroxide is going to run out. And because of that 1:2 ratio, that means that 0.0343 moles of magnesium hydroxide reacts with double the amount of nitric acid. So that means we need to work out what 2 times 0.0343 is to work out how many moles of nitric acid have reacted. So that's 0.0686 moles of nitric acid that has reacted, that are no longer there anymore. As a result of this, we now need to work out how much nitric acid then is remaining. And that's going to be found by doing 0.3 minus 0.0686. That leaves us with 0.2314 moles. Now, because we also know the volume that this is in, we have enough information now to get the concentration of this remaining nitric acid. So we're going to use the equation that states concentration is moles over volume times 1000. So that's going to be 0.2314 over 200 and then times by 1000. So that gives me 1.157, which, looking at our answers, if I round that to 2 decimal place, is 1.16. And A is our answer. The mineral chromite can be extracted from natural ore deposits. Pure chromium that can be extracted from this has a wide range of industrial uses due to its variety of colours, high stability and its resistance to corrosion. 1 tonne of ore was mined and it was found to contain 45% chromite. Calculate the mass of chromium in kilograms that was extracted. Give your answer to 3 significant figures. So, first thing that we want to do here is work out if we have 1 tonne of ore, well, what is the mass of chromite that we have? Well, let's start then by writing down what 1 tonne is in kilograms. We should know that 1 tonne is equal to 1000 kilograms. So now that we know this, we can work towards working out what the mass of 48% of this 1,000 kilograms is. So 1,000 times by 0.48, or you could times it by 48 over 100, is going to give you 480 kilograms. Now that is the mass of chromite that we have. However, this question, it's not asking us to find the mass of chromite. It wants the mass of chromium that was extracted. To do this, we need to look at the chemical formula for chromite. So that's FeCr2O4. Let's start by working out what the MR of this chromite is. So to do that, let's check out the periodic table. We can see that the mass of iron is 55.8, plus 2 times the mass of chromium, which is 52, plus 4 times 16 for the oxygen. So putting that into the calculator, I find that the MR of chromite is 223.8. So we're being asked about the chromium. If we look at this formula, we can see that a fraction of it is chromium. 2 times 54 is the mass of chromium in 1 mole of chromite. So if we work out the fraction of chromium in this chromite, we can then use that to work out the mass of chromium. So we've got 104, the chromium, over the total mass, 223.8. If we then want to get the mass of chromium, then we take the mass of the chromite, that's 480, and multiply it through by this fraction. We multiply it by 104 over 223.8. Now putting this into the calculator, I get the mass of chromium to equal 223.0563003 kilograms. Now here we're asked to write it to 3 significant figures, so rounding this I get 223 kilograms, and that is the mass of chromium in kilograms. Chromium has 4 isotopes. Here we're asked to state the number of protons and neutrons in chromium-52. So to be able to answer this, we need to go to the periodic table to see what the proton number or the atomic number of chromium is. So if I have a look in the periodic table, I see that chromium has a mass number of 52.0, and I see that it has proton number or atomic number of 24. Now that number, the atomic number, is equal to the number of protons that an atom has. So we'll use the proton number or the atomic number to say that we have 24 protons present. So now to get the number of neutrons, we need to take the mass number, and remember that the mass number is equal to the sum of protons plus neutrons. So for that reason, to get the number of neutrons, all we need to do is to take that mass number and subtract the number of protons. So the number of neutrons, therefore, is equal to 52 minus 24, and that gives us 28. So that means that we have 28 neutrons in an atom of chromium-52. So now, next part, we're asked to calculate the relative atomic mass of chromium, and we want to give our answer to 1 decimal place. So first things first, let's just remind ourselves of generally how we calculate this. The relative atomic mass is equal to the percentage times the mass, plus percentage times the mass, plus, and then we do it for as many isotopes as we have, and then we divide through by 100. So in this case then, the relative atomic mass is going to be 4.3 times by 50, and then we're going to add on to that 52 times by 83.8. And then after that, we will do it for the next isotope. So that's going to be 53 times by 9.5. And then we do the same for the final isotope. So we add on 54 times by 2.4. So we're going to add all of those together, and then we're going to divide it through by 100. So if I work out what all of those bits on the top of that fraction make, so I'm just going to put it into the calculator, and I get 5,205.7, and that's divided by 100. So remembering that we need to give our answer to 1 decimal place, our answer is 52.1. So that is the relative atomic mass of chromium. Chromium ions are usually found in the +3 and +6 oxidation states. The electron diagram below is partially filled in for chromium 3+. Here we're asked to complete the diagram by showing the missing subshell identities and electron occupation for chromium 3+. Well, we know that chromium has 24 electrons. We should be familiar with that information. So if we were just to start now by doing the electron configuration of just chromium, we are going to remember that it has 24 electrons. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. So this is what it looks like for chromium. For chromium 3+, on the other hand, to become chromium 3+, the chromium must have lost 3 electrons. We need to remember that it's first going to lose electrons from the s subshell. So it loses both electrons from that s subshell, and then it loses the third electron from the d subshell. So that leaves us with 1s2, 2s2, 2p6, 3s2, 3p6. We now have an empty 4s subshell, and then 3d3. So when it comes to filling this in, the next subshell is going to be the 3s subshell. And as we can see here that there's 2 electrons in it, so that is full. So we're going to put 2 electrons in. The next subshell is the 3p subshell. So we fill that in next. Again, we can see that's full with 6 whole electrons. So we've got 1, 2, 3, 4, 5, and 6. Now remember, there would have been a 4s subshell here. That is lower in energy than the 3d subshell, and so we lose the electrons from there first. So we're just going to write 4s here, but we're not going to have any electrons in that subshell. Finally, we have the 3d subshell, and that has 3 electrons in it. So we're going to fill it in 1, 2, 3. Now make sure that you don't double fill any of these. It's important that you remember that each electron goes into an orbital singularly, waiting until all of those orbitals are single filled before it goes back and double fills. That's because the electrons will experience a repulsion if there's 2 electrons in the same orbital. So they will choose to go into their own little orbital if they can, rather than double filling. A chemist carried out some test tube reactions of the Cr3+ ion, as shown in the flow diagram below. Here we're asked to draw a 3D diagram of this particular complex ion. We should recognise that it has a central metal ion of chromium, and we can see that it has 6 water ligands. Now, because it has 6 water ligands, it is going to form an octahedral shape. I always like to start by putting the central metal ion and then surrounding it with that shape before I fill in the ligands. When I bond those ligands to it, I'm going to be really conscious of making sure that the oxygen of that water is bonded to each of the sticks, because it's the oxygen that's donating the lone pair of electrons to form that coordinate bond. So then we're going to stick some square brackets around it and a little 3+ in the top right hand side. Now we're asked to state the colour of this complex ion. So we should recognise that this has a violet colour. So if you're not familiar with this colour for this particular ion, then I recommend you stick it on a flashcard. Now we're told that the bonding of the water in this complex is a dative covalent bond, or a coordinate bond. We're asked to describe what's meant by a dative covalent bond. We should know that in a dative covalent bond, both of the electrons within the covalent bond is donated from one of the bonded atoms. And the way that this is different is normally in a covalent bond, one electron comes from one atom and the other electron comes from the other. But that's not the case in these dative covalent bonds. Both electrons get donated by one of the atoms. So now we're asked to give the formula of substance A. So let's remind ourselves of what substance A is. Here you can see it's formed by adding an excess of ammonia to this CrH2O6 3+ ion. So we should know that when we add an excess of ammonia to this, what happens is a process called ligand substitution. The ammonia also acts as a ligand because it also has a lone pair of electrons on the nitrogen. So what's going to happen is all of those water ligands are going to get replaced by the ammonia ligands, giving us CrNH3 6 3+. Still has the same charge because ammonia, just like water, has no charge. So now we're asked to give the name of the type of reaction that forms substance A. As I mentioned just then, it's a process called ligand substitution because the water ligands are directly substituted with ammonia ligands. So now we're asked to construct a balanced ionic equation for the formation of substance B from CrOH3, and we need to include state symbols. So looking at our flowchart here, we can see that adding an excess of sodium hydroxide to CrOH3 makes our substance B. Now, what we're going to form in this case is going to be CrOH6, which is aqueous, and it has a charge as well of 3-. So what our equation is going to look like is CrOH3 solid plus 3 OH minuses, which are all aqueous, makes this complex ion CrOH6 with an overall 3- charge. And that is also aqueous because it's now an ionic substance. The reason why the charge has changed like this is because we had a neutral substance, something with 0 charge, and we added 3 negatively charged hydroxides to it. That's what has caused it now to have this 3- charge. And there we have it, that is our balanced equation. If you don't know that, that is one that we need to learn, so start adding it to your notes. I always think that transition elements is almost like organic chemistry in that you just have to memorise a lot of facts. And without those facts, you can't really access the questions. So although there's a lot of understanding in chemistry, gosh, if you don't memorise a lot of these facts, even if you understand it perfectly, you're still going to be lost and unable to get those marks. So please don't underestimate the importance of memorising facts like these. Now the next part is another bit we need to memorise, so really proving a point here. Next up, we're asked to state the colour of substance B. So we should know that this CrOH6 with a 3- charge has a colour of dark green. So we just need to get that memorised, that that has a dark green colour. This question looks at the chemistry of sodium oxide, Na2O. It's a white powder at room temperature. So now we're asked to name the structure of sodium oxide. So here we need to know that sodium is a metal and oxygen is, of course, a non-metal, oxides of oxygen. So the structure of this, because it's a metal with a non-metal, is going to be a giant ionic lattice. Remember, we always have ionic bonds when we have metals with non-metals, and you only get giant ionic lattices. So now we're asked to construct a dot and cross diagram of sodium oxide, showing only the outer electrons. Well, let's remind ourselves of this formula. So we've got Na2O. We know it's 2 sodiums for every 1 oxygen. We know sodium is in group 1 and oxygen is in group 6. And therefore we know that sodium is going to have 1 electron in its outer shell. Now that 1 electron that it has in its outer shell can get lost. By losing that 1 electron, it's going to be able to get a full outer shell. It's way easier to get rid of 1 electron than to gain 7. So at the same time, the group 6 oxygen has 6 electrons in its outer shell. So for oxygen, it's much easier to gain 2 electrons than to lose all 6 to get its full outer shell. So with oxygen, we know it has 6 electrons, but then it's going to gain 2 electrons. And it's getting those 2 electrons from each of the 2 sodiums. We had 2 sodiums, each of those is giving up 1 electron. Now that makes the sodium ions positively charged because they've lost the negative electron. And that makes the oxygen ion 2- because it has gained 2 negative electrons. A partially completed Born-Haber cycle for the standard enthalpy change of formation of sodium oxide is shown on the next page. Here we're asked to define the term standard enthalpy of formation, and this is a definition that you need to get memorising if you don't already know it. So we should know that the standard enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its elements under standard conditions. Now there's 2 really important points you need to include there to get your 2 marks. The first point that you need to include is the fact that it's 1 mole of a substance. And this is true of any definition that involves enthalpy. We always have this 1 mole element to the definition. The second part of the definition that we need to make sure that we state is that it forms from its elements under standard conditions. It's not just anything it's forming from, it's its elements. And because it's a standard enthalpy change of formation, it does have to be under standard conditions, not just any conditions. Now in part 2, we're asked to give those standard conditions. So these are more things we need to get memorising. We should know that the standard pressure is 100 kilopascals. Alternatively, you could call that 101 kilopascals or 1 atmosphere. And the standard temperature is 298 Kelvin, or of course you can write that as 25 degrees C. Now to get the mark here, you need to give both of those standard conditions. Here we're asked to complete the Born-Haber cycle using information in the table and to use this information to calculate first ionisation energy of sodium. So first things first, let's complete this diagram. So let's start by filling in this blank here. We should recognise this downwards arrow as showing the formation of sodium oxide. So we need to have the elements in their standard states here. So that's going to be 2 Na solid plus a half O2 gaseous. So we filled in that one by knowing that that's showing the formation of sodium oxide. So now let's look at this other blank. So there's actually 2 options to what you can say here. If we compare underneath this line with above this line, we can see both the sodiums and the oxygens have changed. So either we can ionise the sodium or we can atomise the oxygen here. Here I'm going to choose to atomise the oxygen, but you will get the mark whichever option you choose. So here I'm going to say we've still got the 2 Na gaseous, but we have atomised the oxygen, leaving us with just O gaseous. So now we need to calculate that first ionisation energy of sodium. So let's highlight where that is and let's label it with an X. That's what we need to find. So to be able to do this, let's start off by labelling on the diagram all of these different enthalpy changes. So I've started here by labelling on the enthalpy of formation of sodium oxide. So I've written minus 414.8 next to that arrow. Next up, let's do the atomisation of sodium. Here you can see that we need to atomise 2 sodiums to make gaseous sodium. So having a look at our numbers, I can see that the atomisation of 1 mole of sodium is 107.8, but we need to double this to account for the fact we have 2 moles of sodium. Okay, so the next arrow now is going to look at the atomisation of oxygen. So here I only make 1 oxygen through this atomisation. So I just put 249. I'm not making 2 oxygens, I'm just making 1. So the next arrow that we can label is the one that shows the electron affinity of oxygen. We've only got 1 oxygen made there, and so we just put minus 141 next to that. So next up, our next arrow is the second electron affinity of oxygen, and again we've just got 1 of those, so we've got 797.7. And the last arrow, this big arrow here, shows the lattice enthalpy of sodium oxide. So that is our 2528.3. So we've labelled everything there, we've considered where we need to double things and so on, and we need to find this X. Now the way that I like to think of these, but there's lots of other ways you can use, is I like to think, what's the start and the end of this arrow that I'm being asked to find? I know, due to Hess's law, that it doesn't matter which route we take, the enthalpy change will be the same. So if I go the long way round here, I will end up getting the same enthalpy change. So that's what I'm going to do. I'm going to follow this long route round to be able to calculate my enthalpy change x. So let's get started. So starting at that start point, I'm going down, and that's opposing the direction of that arrow. So I'm going to do negative 249. I've reversed the sign because I'm opposing the direction of the arrow. So next step down, I'm again opposing the direction of the arrow. So I'm going to do minus 2 times 107.8. Down again, but this time I'm going in the same direction as the enthalpy change. So I'm just going to write it as it is. I'm going to write minus 414.8. Okay, so now on to the next leg of our journey. I'm going up, and I'm going in the same direction now as this enthalpy change. So again, I'm just going to write it as I see it. I'm going to add on positive 2528.3. Next leg of the journey now, I'm going downwards, and I'm opposing the direction of the arrow. So I'm doing negative 797.7. The last part now, I'm going up, and I'm opposing that enthalpy change. So I'm going to reverse the sign of the minus 141 and make it positive 141. So now if I tap this all into the calculator, I will find what x is. So here I get that x equals 992.2. Now we're being asked to find the first ionisation energy of sodium. Notice here though, x is representing 2 of these first ionisations. So for that reason, we need to take our value of x and we need to halve it to find out what one ionisation energy is. So 992.2 divided by 2 gives us our enthalpy change. It gives us 496.1 kilojoules per mole. And so that is our first ionisation energy of sodium. Now we're asked to explain why the value of the first ionisation energy for potassium would be different to that of sodium. Now compared to sodium, potassium's first ionisation energy decreases. The reason for this is that potassium has more shells and therefore it has more shielding. Now the knock-on effect of this is that we're going to have a weaker attraction between that outermost electron and the nucleus, and therefore that outermost electron is easier to remove and it's going to require less energy to remove. Now that's why the first ionisation energy has decreased. And those are the 3 points we want to state to get our 3 marks. Sodium oxide reacts with water to form sodium hydroxide. This reaction gives out heat. Here we're asked to draw an enthalpy profile diagram for this reaction and to label the enthalpy change delta H. Well, importantly here they tell us that the reaction gives out heat. This means that this is an exothermic reaction, and that's going to determine the shape of our enthalpy profile diagram. So we're going to start by writing down the reactants, Na2O plus H2O on a line. And because it's exothermic, our products are going to be lower down. So we're going to write beneath it and further to the right 2NaOH. So this question specifically wants us to label the enthalpy change. So I'm going to do an arrow going downwards from the reactants to the products, and I'm going to label that delta H, the enthalpy change. Sodium oxide shows basic behaviour and thus reacts readily with acids. An example is the reaction of sodium oxide with hydrochloric acid solution to form sodium chloride and water. The table below shows some data for the enthalpy of formation of these substances. Using information in the table, calculate the standard enthalpy of reaction for the reaction of sodium oxide with hydrochloric acid to form sodium chloride and water. Okay, so the first thing that I like to do is just to write out my balanced equation along the top. Make sure it is balanced, otherwise we're going to not get this right, okay? So we've got our nice balanced equation. We know that it makes sodium chloride and water, and to balance this we need 2 HCl's and 2 NaCl's. Now what's important is what data they give you to calculate this. Here I can see they've given me enthalpy changes of formation. That tells me I need to do a Hess cycle using those values. That means I'm going to put the elements on the bottom and I'm going to draw two arrows going up from those elements to form the things on the top, okay? The direction of those arrows is really important. Now I'm just going to go through each of these substances and I'm going to fill in next to those arrows those enthalpy changes. So I have one sodium oxide, so I write minus 414.8. I have two HCl's, so I do 2 times minus 92.3. Then over on the other side, I have two sodium chlorides, so that's 2 times minus 411.2, and then I add the minus 241.8 for the water. Now, to stop me making any mistakes later down the line, I will now simplify each of those little bits next to the reactants and the products. So for the reactants, I get minus 599.4, that's just adding them together, and for the products we get minus 1064.2. Now, because of Hess's law, remember it doesn't matter which route we take, we can use different routes and the enthalpy change will be the same. So this is what we're going to do here. If we go from the start point, we can go down and then up, and we end up at that same end point. So let's use that, and let's use the numbers to calculate this enthalpy change. So if we start on our journey by going down, notice we're going in the opposite direction to that green arrow. That means we need to reverse the sign of this minus 599.4 and make it positive. So then we're going to go up to get to our end point here. By going up, we're going in the same direction as the green arrow, so we're going to keep the sign of that enthalpy change the same. So what we're left with here is 599.4 minus 1064.2. Now popping that into my calculator, I get my answer for my enthalpy change of reaction to be minus 464.8. And that's all that we need to do with Hess's law. It's not as bad as it seems. If we have an enthalpy change of formation question like this one, I would just start by writing my balanced equation along the top, write down elements on the bottom, and have two arrows going upwards from those elements to my equation above. And then I will just fill in all of the data for the enthalpy changes of formations of the reactants on the left-hand side and the products on the right-hand side. And then I would just use the idea of Hess's law that it doesn't matter which route we take, the enthalpy change will be the same to calculate my enthalpy change. And that's all there is to it. We can apply that to all sorts of different questions. The Passerini reaction, discovered in 1921, is an exciting example of a multi-component organic chemical reaction. Here is an example of a Passerini reaction. With reference to atom economy, explain why the Passerini reaction is considered highly efficient. So they've mentioned atom economy here. This particular reaction I can see has 100% atom economy because there's only one product. All of those reactants make one product, the product that we wanted to make. So the reason why this Passerini reaction is considered highly efficient is because all atoms from the reactants are in the product. There's only one product. And therefore we can state that we have 100% atom economy. And this is why this reaction is considered highly efficient. In 1951, the kinetics of the Passerini reaction was studied to determine the overall rate order. A student was given some example experimental data for a Passerini reaction. The experiments were all carried out at the same temperature, and the results were shown below. So here you can see we've got a rate concentration graph and a table, and we're told that using the experimental information provided, we're asked to explain how the reaction orders of the reactants in the Passerini reaction can be determined, and use this to find the rate equation and calculate the rate constant and its units. So it's a 6 marker here. We've got a lot of things we need to do to get our marks. The first thing I would do is just look at this graph. I can see that here the rate and the concentration of CH3CHO is directly proportional. So for that reason I can deduce that this reaction will be first order with respect to CH3CHO. So we've already worked out the order with respect to that reactant. So now let's have a look at some of the other information. Let's have a look at the table and let's try and find out the rate with respect to this ethanoic acid. If we compare experiments 1 and 3, we can see that the concentrations of the other reactants are constant, so the only concentration that changes is the ethanoic acid, which means it has that direct effect on the rate. I can see that the concentration has doubled, and I can also see that the rate has doubled too. So we should know that when concentration doubles and rate also doubles, we need to know that the order is first order with respect to ethanoic acid in this case. So we've figured out another order here, we're doing good. So now let's have a look at something else in this table. Let's try and work out the order with respect to CH3NC. If we compare experiments 2 and 3 here, we can see that the concentrations of ethanoic acid has stayed the same, and the concentration of CH3CHO has also stayed the same. So that's going to be the pair of experiments that we need to compare here, experiments 2 and 3. So if we have a look at how the concentration changes going from experiment 2 to 3, we can see that it's got 4 times smaller. So we could say that it's been times by a quarter. Now let's do the same thing with the rate comparing 2 and 3. Again, I can see it's got 4 times smaller. So I'm going to say that the rate is times by a quarter again. So the same reasoning as before. Because the concentration has changed and the rate has changed by the same amount, we can say that this reaction is first order with respect to CH3NC. So now we know the orders of all 3 of the reactants. This enables us to write down the rate equation. So we know that rate is equal to K times by the concentrations to the power of their orders. So this is going to be rate equals K times by the concentration of CH3CHO to the power of 1, but we don't need to write that. And then times by the concentration of ethanoic acid, again to the power of 1 because that's the order, but we don't need to write it. And then finally the concentration of CH3NC, and that would again technically be to the power of 1. There we have our rate equation. Now the next thing that this question wanted was for us to work out the rate constant. So in order to work out the rate constant, we need to rearrange this equation. So K is going to be equal to rate times by all 3 of those concentrations times together. Then what we want to do is to put some data in. So we can either use the data from experiment 1, 2 or 3. It's going to give us the exact same outcome. I'm going to use experiment 1 just because why not, it's there. And so here I'm going to say 6.25 times 10 to the minus 7 for the rate, and then divided by all those concentrations times together. So I've got 8.75 times 10 to the minus 4, times by 5.50 times 10 to the minus 4, times by 3.65 times 10 to the minus 5. So this is going to give us our rate constant. Once we put that into our calculator, so I end up finding that K is equal to 35,580.8575. So there we have our rate constant. However, we need to give the units to that rate constant as well. So to find the rate constant's units, what we want to do is to use the formula for the rate constant and substitute in the units of the rate and of those concentrations. So the unit for rate is moles per decimeter cubed per second, and the unit of each of those concentrations is moles per decimeter cubed. So on the bottom we have moles per decimeter cubed times by moles per decimeter cubed times by moles per decimeter cubed. So now let's cancel what we can. I can cancel 1 mole and one of the dm-3s on the top and the bottom. So that leaves me there with on the bottom moles times by moles, which I know gives me moles squared. Because that's on the bottom though, I'm going to write that in the units as mole minus 2. I reverse the sign. Then I've got dm-3 times dm-3, which gives me dm-6, which again, when writing it as our units, I reverse the sign. So that's dm to the power of 6. And then finally, I've got s to the minus 1, which isn't on the bottom of this fraction, so I'm just going to write s minus 1 in my units. So here, my value of k is equal to 35,580. We could say 0.8575. You can round that, of course, at any particular point that you fancy, so long as you round it correctly. And then we've got mole to the minus 2, dm to the power of 6, s to the minus 1. And there we have it. We've got the rate equation, we've got the rate constant, and we've got the units for that rate constant. So this method can be applied in all sorts of questions. Keep an eye out for this. It's a very common type of question. Boron-mediated reactions are another example of multi-component reactions. Unlike the Passerini reaction, some BMRs are reversible. A reverse BMR was investigated at different temperatures and the rate constant was calculated, and it was found to be a first-order reaction. The results are shown below. Here we're asked to explain why the rate constant increased with increasing temperature. Well, the first thing we should recognise here is that if the rate constant increases, that means that the rate also increases. They're directly proportional. And so that means that the reaction will happen faster. So now we can link this with increasing temperature. We know that as temperature increases, the particles have more kinetic energy. And as a result, we have more frequent successful collisions. Now the reason why this is going to increase the rate of reaction then is because the proportion of particles which are going to have an energy greater than that activation energy when they collide is going to increase. So this is why that rate of reaction increases. And then of course the rate constant is directly proportional to the rate as well. So this is why increasing the temperature increases the rate constant. Here we're asked to complete the table. I've just put it here next to us and plot the data on the graph below. Use the graph to calculate the activation energy for the reaction and give your answer in kilojoules to 3 significant figures. So first things first, let's have a go at completing this table. So you can see we need to complete the 1 over temperature column first. Notice though, really importantly, it says times 10 to the minus 3 up there, which means that that's been removed from the numbers in the column to make it look a bit nicer basically. So when we start with the first number here and we do 1 over 323, what we actually end up getting is 3.095975 times 10 to the minus 3, okay? So we're taking that times 10 to the minus 3 out, and then we're just going to write down here to 2 decimal places to be consistent with what is in this column, 3.10. So then let's repeat the same. So this time let's do 1 over 313, that's the next one. So to 2 decimal places, that gives me 3.19 times 10 to the minus 3. So again, I'm just going to put down 3.19. And then if I now do 303, do 1 over that, I get 3.30 times 10 to the minus 3. So I just pop 3.30 in my column. So now for the next column, I've got ln k. That means I want to do ln of all of these different rate constants. So starting us off, I do ln of 4.10 times 10 to the minus 4, and I get minus 7.8. I do the same for the next one, I get minus 9.1, and the last one I get minus 10.5. So that's from doing ln of 2.75 times 10 to the minus 5. So purely just substituting in the relevant numbers. So now we need to plot these points, okay? So we'll start by plotting the point of 3.00 and minus 6.3. So we're going to make sure that we do that, and we're going to do a little point. We're going to make sure that we use a pencil in the exam. And so here we go, this is what I get. So now I'm going to plot the point of 3.10 and minus 7.8. I'm going to put that point down, make sure that I read the scale correctly, because that would be a really easy place to lose some marks. I've got my point there. Again, I'm going to be using a pencil in the exam. Then I do it for 3.19 and minus 9.1. And again, I just simply plot that point on my graph, making sure I use a pencil in the exam. So now I'm going to plot the next point, the point which is at 3.30 and minus 10.5. So nice and straightforward, relatively speaking, to plot this one. So I'm just going to pop it down just here. And finally, I'm going to do the point 3.41 and minus 12. So again, being really conscious of the scale of this particular graph, I'm going to plot that point here. So now in the exam, I'm going to get my ruler out and again my pencil, and I'm going to draw my line of best fit. Fortunately here, it looks like this line will go through all of the points. So great, I've got my line of best fit now. And now it's a case of, well, why do I need this, okay? So in your datasheet, they give you the Arrhenius equation in a nice rearranged form, which is going to enable us to compare it to y equals mx plus c. So the equation that we're going to get from our datasheet states that ln k equals minus EA over RT plus ln A. And in this question, we're being asked to find the activation energy. We compare this to y equals mx plus c. We can see that the y-axis has ln k on it, so that's our y. We can see that our x-axis has 1 over t on it, so 1 over t is our x. Now by comparing these now, we can see that the gradient is going to be that minus EA over R, which means that if we calculate the gradient of this line, we can take that value for the gradient and equate it to minus activation energy divided by R. That means we need to get our gradient then, okay? Make sure that you always do a really big triangle to be able to work out your gradient. The bigger the better, there's going to be less errors in your calculation and it's going to be more accurate. So I've chosen this. So I can see that the difference in the y-axis is between minus 5 and minus 12, and the difference in the x-axis is between 2.9 and 3.41, but really important, this is where people lose marks. See hidden there, times 10 to the minus 3. We can't just do the difference between 2.90 and 3.71. No, it's got to be between 2.90 times 10 to the minus 3 and 3.41 times 10 to the minus 3. Okay, so gradient then. The change in y. So I'm going to do here minus 12 minus 5. Now the point corresponding to that minus 12 is that 3.41 times 10 to the minus 3. So I'm going to do that minus the 2.90 times 10 to the minus 3. Notice there that the order does matter because it's going to get you the correct sign for the gradient. So I end up getting there minus 13,725.5. Now, if you didn't get a negative, you can always just look at this and see it's clearly a negative gradient and just add this on, but don't forget that. So now we can equate our gradient to minus EA over R. Now, because they're both negative, we can just ditch the negatives, okay? And if we multiply the gradient by 8.314, our value of R, notice that that gives us our activation energy. So here I get the activation energy is equal to 114,109.65 joules. Activation energy calculated using this way is always going to get the activation energy in joules. However, more often than not, they will want it in kilojoules. So this means we need to convert it to kilojoules and then round it to the 3 significant figures desired. So the way that we convert joules to kilojoules is simply by dividing through by 1000. So in that case, when we round this to 3 significant figures, we find that the activation energy is equal to 114 kilojoules, and that there is our answer. So just to mention, there's a chance that you might have got a slightly different answer if you did this yourself. However, remember that this required us to work out the gradient of this line, and there's always going to be a little bit of room for error, not even error, just give or take a little bit when calculating that gradient. You know, we're not computers, we're not going to do it perfectly. So for that reason, they will always allow a little bit of leeway in the answer here. So if you got slightly different to 114, which I did, that's fine. So long as it's not massively different and it's just out by a few kilojoules, you will still get awarded your marks. The table below shows some standard electrode potentials. From the table, identify the letter of the redox system that is the strongest oxidizing agent. So here we need to know the fact that the most positive electrode potential represents the strongest oxidizing agent. And so if we look at this table here, we can see that F has the most positive electrode potential, and therefore that is the system that's the strongest oxidizing agent. So now we've got this question here. So a cell was made using redox systems C and E. So let's highlight these now so that we know which ones we're talking about. Now we need to draw a label diagram of the apparatus needed to measure the standard cell potential of this cell. So to be able to answer this, we need to think of the little systems within it. So looking at C first, we've got Li plus aqueous plus an electron makes Li solid. So whenever we've got a solid part of these half equations, that's going to be the material that we use for the electrode. And whenever we've got something aqueous, that's what we put in the solution. So we know in one of these half cells, we're going to have a lithium electrode and a solution of Li plus ions. Then looking at the other system within it, we've got zinc 2 plus 2 electrons makes solid zinc. So like with before, because we've got a solid part of this half equation, we can identify what the electrode will be made of. We're going to have a zinc electrode here. And we've got some aqueous as well, so we know that we need a solution with zinc 2 plus ions in it. So now we can start drawing. So to start with, we're going to have a beaker and a second beaker. In the first beaker, we have a solution, and we're going to label that solution as containing Li plus ions. The concentration of this will be 1 mole per decimeter cubed because we need the standard cell potential. Next up, we're going to draw, dipping into this solution, a solid lithium electrode. And we've completed that half of it now. Now let's go on to the other side. In this case, we're going to have a zinc solid electrode, and the solution would be Zn2 plus. And like we said before, we need a concentration of 1 mole per decimeter cubed. So now dipping into each of the two solutions is going to be our salt bridge. Make sure that you label this salt bridge. And finally, connecting the two electrodes is going to be a wire and a voltmeter. So we're going to draw a wire connected the first electrode to the other electrode with a voltmeter in the middle. Now that there is our label diagram of the apparatus needed to measure the standard cell potential of this cell. A cell was made using the nickel 2 plus system and the iodine system. Using the data in the table, calculate the standard cell potential for this cell. So I'm highlighting those two now. We should know that to calculate the standard cell potential for a cell, we want to take the most positive of the two and subtract the most negative. Now these don't have to be positive and negative, they could both be negative like in this case, but the most positive of the two, which in this case is the minus 0.26, and we will subtract the most negative of the two, which is minus 0.54. And if we put that into the calculator, we will get 0.28 volts, which is positive, and we will always expect to get a positive answer in these questions. So now we need to write an equation for the overall cell reaction of this cell, so still the one containing the systems A and B. Now, here are the steps that I would use to do this. First thing that I would do is I would look at those, and I would flip the most negative of the two, the one with the most negative electrode potential. Next up, I'm going to check the electrons in both of these two equations and see if I need to balance them at all. Now looking at this, I can see they both have 2 electrons, so I won't need to, but often we will need to multiply up by a factor to make them balance. And then finally, I essentially just smush them all together. I will cancel anything that they both have in common, but all of the reactants combine and all of the products combine. So let's put that into practice so that you can see what I mean. So I'm going to start by flipping the most negative of these two. So instead of it being I2 plus 2 electrons goes to 2I minus, here I've written it as 2I minus goes to I2 plus 2 electrons. I've flipped it. So now I'm writing the other equation next to it, just underneath it, and I'm going to check if the electrons are balanced. I can see that they both have 2 electrons, so yes, they are balanced, and I can move on to the next step. Now I want to smush them together. Okay, so I am going to draw this imaginary line that separates the reactants with the products. I can cancel anything that appears on either side. So there's 2 electrons on the left and on the right, I will cancel those. And now I'm just going to write down what's left of the reactants. So here I've got 2I minus plus Ni2 plus, and that's going to go to all of the products that I have left. So that's going to go to I2 solid plus nickel solid, which are those 2 parts that we have left when we smush together the products of these equations. And that's it. That is our equation for our overall cell reaction. And those are our 3 steps that we need to know to be able to identify it. I think that there's a lot here that we could go away, turn into a flashcard. Make sure that you know how to calculate the standard cell potential, so the most positive electrode potential minus the most negative, and make sure you know how to get that overall cell reaction by first flipping the most negative, then balancing any electrons if they're not balanced, and then smushing them together. Good work. A student was investigating the differences between solutions of sulfuric acid and ethanoic acid. They added calcium hydroxide solution to each test tube. Here we're asked to construct a balanced equation for the reaction of sulfuric acid with calcium hydroxide solution. Well, here we have our classic acid plus a base makes a salt plus water. So we know that we have sulfuric acid, and we know it's reacting with our base of calcium hydroxide. Both of these are solutions. Acids will always be solutions, and here we're told that it's calcium hydroxide solution, which is how we know that's aqueous too. So like I mentioned before, we know an acid plus a base makes a salt and water. Well, in this case, when we react sulfuric acid with calcium hydroxide, we end up making a calcium sulfate salt. We know calcium has a 2+ charge and sulfate has a 2- charge. That means that the formula for calcium sulfate will simply be CaSO4. Now, knowing our solubility rules, we should be familiar with the fact that calcium sulfate is a solid, so that is the state of that substance there. And finally, we make water as well, and we should know that water is a liquid. Now, looking at this, we need to balance it. We've got sulfates on each side, 1 of each, so that's fine. But we have 4 hydrogens on the left. And we also have 2 oxygens unaccounted for that weren't within the sulfate. And so therefore we're going to need to multiply the waters by 2 to then account for those hydrogens and those oxygens. So what we have here now is our balanced equation complete with state symbols. They observed a more vigorous reaction with the sulfuric acid and concluded it was a strong acid and the ethanoic acid was weak. Explain what's meant by the term strong and weak acids. Now this is a very important set of definitions, so if you don't know them, please do make some notes on them now. So we should know that a strong acid is an acid which will fully dissociate into its ions in water. Some examples of strong acids are sulfuric acid, hydrochloric acid and nitric acid. We should be able to identify those as strong acids. So next up, let's see the definition for a weak acid. So unlike the strong acid, a weak acid is an acid which will only partially dissociate into its ions in water. Now we should recognise that all of the carboxylic acids are weak acids, and also phenol acts as a weak acid as well. So it's important we can recognise which acids are weak, which are strong, because if we need to make calculations later down the line, that will be dependent on that knowledge. Okay, so the pH of the reactions was monitored with a pH meter. it was observed that the final pH was greater than 7. State what this implies about the calcium hydroxide. Well, a pH greater than 7 means that it's more alkali. Now, if we had the same amount of hydroxide and sulfuric acid, then they would have balanced out and just formed this neutral substance because we would have had a salt solution remaining at the end. However, if we've got a pH greater than 7, and therefore it's a bit alkaline, that must mean that all of the acid got used up and you were left with an excess of the calcium hydroxide. So we had some remaining that was going to be left in the solution, making it a bit alkaline still. So to answer this question, what does this imply about the calcium hydroxide? It implies that it must have been in excess. The pH meter needs regular calibration. To do this, buffer solutions of a known pH are used. The student needed to prepare 125 centimetres cubed of a buffer solution of pH 3.75 from ethanoic acid and its salt sodium ethanoate. The solution of ethanoic acid was 0.5 moles per decimetre cubed, and the Ka of ethanoic acid is equal to 1.74 times 10 to the minus 5. Here we're asked to calculate the mass of sodium ethanoate required. Okay, so this is a buffer question. These are very common and they're often worth a lot of marks. First thing I'm going to do is I'm just going to write down that dissociation of my ethanoic acid. So ethanoic acid dissociates to make H plus CH3COO minus. Now I've got this, I'm going to write my Ka equation for ethanoic acid. Ka is going to equal H plus in square brackets times by the concentration of CH3COO minus divided by the concentration of ethanoic acid. Now, in this question, we know quite a lot of things, or we can calculate certain things. Because we're being asked to calculate the mass of sodium ethanoate, eventually we need the concentration of CH3COO minus to help us. We know in the question what the pH is. We can use the equation concentration of H plus equals 10 to the minus pH, or in this case 10 to the minus 3.75, to find that the H plus concentration is 1.778 times 10 to the minus 3. Now that we know that, we know one of the parts of this equation, which is going to help us find that concentration of CH3COO minus. We're also told that Ka equals 1.74 times 10 to the minus 5. So that's another part that we know in this equation. And finally, we were told that the solution of ethanoic acid had a concentration of 0.5 moles per decimetre cubed. So we know another thing in this equation then. So actually, we know 3 of the parts of this equation, and we need to find that concentration of CH3COO minus. Well, actually, we can just rearrange this equation now, can't we, to find that. So CH3COO minus will equal Ka times by the concentration of ethanoic acid divided by the concentration of H plus. So there we have it. If we put the numbers in here, we'll find that the concentration of that ethanoate ion is 1.74 times 10 to the minus 5 times by 0.5 over 1.778 times 10 to the minus 4. Now we're going to need our calculator for this. So tapping it away into the calculator, I find that this concentration is equal to 0.04893 moles per decimetre cubed. So returning to the question, I can see I need to calculate the mass of sodium ethanoate. To find that mass, we need the moles. So we know that moles can be calculated by using concentration times volume and then divide by 1,000 to make the units consistent. So here we have 0.04893 times by that volume of 125 and then divide by 1,000 because the units were moles per decimetre cubed and centimetre cubed. That gives us a number of moles for that ethanoate ion equal to 6.11625 times 10 to the minus 3. Well, we need to find the mass of sodium ethanoate. Now, sodium ethanoate has a 1-to-1 ratio with the number of ethanoate ions within it and the sodium ethanoate. So therefore we also know we have 6.11625 times 10 to the minus 3 moles of sodium ethanoate. If we work out the MR as well, we can get the mass. So the MR will be equal to 2 times 12 for the carbon, plus 3 times 1 for the hydrogen, plus 2 times 16 for the oxygen, plus 23 for sodium, and that gives us an MR of 82. So we know, don't we, that mass equals Mr. moles, or MR times by the moles. Here we're going to have 82 times by 6.11625 times 10 to the minus 3. Now when I put this into the calculator, and if I round my answer to 2 decimal places, I get 0.50 grams of sodium ethanoate. And there we have it, that is our buffer calculation. They're all really repetitive, so make sure that you get used to this method, and then they should become quite easy. The Haber process has been revolutionary in its ability to produce industrial scale quantities of ammonia, which can then be used for a wide variety of applications, including agriculture. So the equation for the Haber process is given here. A sealed vessel at a constant temperature contained 3.55 moles of N2, 3.55 moles of H2, and 0.5 moles of NH3 at 350 degrees C. It was left to reach equilibrium. At equilibrium, the number of moles of NH3 was measured to be 1.5 and the pressure was 200 atmospheres. Here we're asked to calculate Kp at this temperature. Okay, so first things first, I'm writing out the balanced equation, and then I'm going to write ice alongside it. So this is my ice method. The I stands for the initial amount. So initially we had 3.55 moles of nitrogen and hydrogen and 0.5 moles of ammonia. So we know at equilibrium we had 1.5 moles of ammonia. Now this enables us to work out the change. We can see that ammonia has gone up by plus 1.0. So remember that these changes use the molar ratios. So here we have got a 2-to-1 ratio between the ammonia and the nitrogen, which means that the nitrogen has only gone down, remember the reactants go down, by 0.5. And due to that 2-to-3 ratio, the hydrogen has gone down by minus 1.5. So this enables us now to work out the equilibrium amounts of nitrogen and hydrogen. So nitrogen is now 3.05 and hydrogen is 2.05. Let's remind ourselves of the equation for Kp. So Kp is the partial pressures of the products divided by the partial pressures of the reactants. So in this case, Kp equals the partial pressure of ammonia, and we always do it to the power of the number of moles. So the partial pressure of ammonia squared divided by the partial pressure of nitrogen times by the partial pressure of hydrogen cubed. So we need to know what the partial pressures of each of these things are. So the way that we work out partial pressure is we take the mole fraction and we multiply it by that total pressure. So first things first, I guess, is we need to work out the mole fractions of each of these components. To work out the mole fraction, we take the number of moles, in this case of nitrogen, and then divide it by the sum of all of the moles present. So in this case, all of the moles present is going to be equal to 3.05 plus 2.05 plus 1.5. So that there gives me 6.6 as my total number of moles. So now we know this, we can say that the partial pressure of nitrogen is going to be equal to 3.05 divided by that 6.5, gives us our mole fraction, and we times it by that pressure, which we're told is 200 atmospheres. So now we've got this, we can tap it away into the calculator, and we find that the partial pressure of nitrogen is equal to 92.42 atmospheres. So now we need to do the same for the rest. Let's do it for the hydrogen now. So first the mole fraction, we take 2.05 and divide it by the total number of moles, so that's 6.6, and we times it by the pressure, which is 200 atmospheres. So in the calculator that goes, and we get 62.12 atmospheres. So now the partial pressure of the ammonia. So that's equal to 1.5 divided by 6.6 times by 200. That gives me 45.45 atmospheres. So now we have all of the partial pressures, we can substitute it into the equation for Kp. So Kp equals 45.45 squared divided by 92.42 times by 62.12 cubed. So that is where our calculator comes into it. So we're going to tap that away, and I find that we get 9.32 times 10 to the minus 5 as our Kp. Now that is given to 2 decimal places and in standard form as required. However, we also need the units. So to get the units, a bit like with Kc, we just substitute in the units instead of the numbers into our equation. So here we get atmospheres squared divided by atmospheres times by atmosphere cubed. Now that leaves us with 1 over atmospheres squared. Now because that squared's on the bottom, it is rewritten there as atmospheres to the minus 2. So Kp equals 9.32 times 10 to the minus 5 atm to the minus 2. The table below provides entropy and enthalpy data for the Haber process. Here we're asked to prove by calculation that the reaction is feasible at 25 degrees C. So to be able to work this out, we need to calculate delta G. Delta G is given by delta H minus T delta S. And the reason why delta G is important here is because reactions are feasible when delta G is less than 0. So we're going to have to calculate delta G for this reaction here and compare that value to 0 to see if it's feasible or not. So the temperature in this case is 25 degrees C. To put it into this formula, we need to convert it to Kelvin. So in this case, by adding 273, we find that the temperature equals 298 Kelvin. So next up, we need to find delta H. Now, delta H is essentially going to be the enthalpy change of this reaction. Now, let's remind ourselves of what reaction we're doing this for. It's for the Haber process, isn't it? So the balanced equation for the Haber process is N2 plus 3H2 makes 2NH3. Now we're making ammonia there. We know the enthalpy change for the enthalpy of formation of ammonia. However, that is just making 1 mole. Here we've made 2 moles of ammonia. So the enthalpy change of the Haber process is 2 times the enthalpy of formation. That represents the fact that yes, we are forming ammonia here, but we're forming 2 moles of ammonia. So in this case then, delta H equals 2 times minus 46, which equals minus 92 kilojoules per mole. So next up we need delta S. So we find delta S by working out the sum of all the entropies of the products and subtract the sum of all of the entropies of the reactants. So here again, this is where having our balanced equation helps. In terms of the products, we have 2 moles of ammonia. So we're going to do 2 times 192.5. And then we're going to subtract the sum of the entropies of all the reactants. So for nitrogen, that's 191.6. And then we add 3 times 130.7. So simplifying all these brackets, I make that 385 minus 583.7. So that gives me a delta S equal to minus 198.7 joules per Kelvin per mole. Now, here is one of the main problems people come up with here. The units for delta S, the standard units are joules per Kelvin per mole, and that's what we will generally be given. However, for delta H, the standard unit is kilojoules per mole. Now, if we want to put these in the same equation, we need to make these consistent. And we can do that by converting the entropy change into kilojoules per Kelvin per mole. And we do that simply by dividing by 1000. So that leaves us then with delta S is equal to minus 0.1987 kilojoules per Kelvin per mole. So now we have all the things that we need to substitute into this equation. We've got the temperature, we've got delta H, and we've got delta S. Please do make sure though, this is your little disclaimer, this is quite a simple question, but people make mistakes all the time, and the most common mistakes are not converting temperature into Kelvin and not making the unit of the delta S and the delta H consistent. Easiest way to do that would just be to take your delta S and divide by 1000. Okay, so let's get calculating delta G now. So delta G will equal minus 92 minus 298 times by minus 0.1987. So that gives us a value for delta G equal to minus 32.7874, and that's in kilojoules per mole. So here we can see that that is indeed less than 0. And so because it's less than 0, it's feasible. And that is our answer, that's our 4 marks there. So now we're asked to explain why that despite the feasibility at this temperature, the usual temperature to conduct the harbour process is approximately 450 degrees. So we could just do this at room temperature. Why aren't we choosing to do that then? Why are we going all the way up to 450 degrees C? Now, this is all about rate of reaction. Yes, indeed, we can still have the reaction happen at lower temperatures, but it's going to take place much, much slower. But this is an industrial process and it's all about the money. We want to make as much as we can, as quickly as we can, and as cheaply as we can. So on balance then, the rate is going to be too slow at 25 degrees, and 450 degrees C has a much faster rate, so that's why they choose that temperature. A student was provided with 4 unknown substances. They were told they needed to carry out a series of tests to identify them. The possible identities were calcium bromide, calcium carbonate, sodium sulfate, and ammonium iodide. We're asked to describe a series of test tube reactions that the student could do to identify the 4 substances. So we need to include all of our reagents, equations, and all observations. Okay, so let's start just by writing out what we have here. So we've got calcium bromide, we've got calcium carbonate, we have sodium sulfate and ammonium iodide. Now let's have a think about what we could test for in each of these cases. We could test for bromide ions to determine that we have calcium bromide. We could test for carbonate ions to prove that we have calcium carbonate. We have sodium sulfate, we could test for the sulfate ions there. And finally we've got ammonium iodide. There's a couple of tests we could do there. We could test for the presence of the iodide ions, or we could test for the presence of those ammonium ions as well. So this here is a good example of what we need to think about. We need to think, what are the tests for each of these substances that's going to enable us then to determine their identity. So the first test that we need to carry out is the test for carbonate ions. So this test is a very simple one. All we need to do is to add an acid. So the acid we should choose here should be nitric acid, because if we used sulfuric acid, we're introducing sulfate ions, and if we introduce like hydrochloric acid, then we're introducing chloride ions. We don't want those. So we're going to add dilute nitric acid, and if any gas comes off there, we're going to bubble it through lime water. We should remember that that is the test for carbon dioxide gas. And of course the reasoning for this is if we react a carbonate with an acid, then we form carbon dioxide, don't we, which we can test for. So now we've explained the reagents and the observations that we will see, let's write down the relevant equation. Of course here we're testing for the presence of calcium carbonate. So we'll have the calcium carbonate, it will react with nitric acid, and we end up forming calcium nitrate and carbon dioxide and water. Now balancing that equation, we need 2 of the nitric acids. But there we have it. There is our equation that we will see when we have calcium carbonate reacting with that nitric acid. Okay, so now let's move on to the sulfate. Let's do the test for sulfate. Now, the test for sulfate ions has two steps. The first step is to acidify the solution, which of course we've already done by adding this nitric acid. And then we follow that by adding barium nitrate. Now, what's going to happen there is the barium is going to dissociate from the barium nitrate, and it's going to react with any sulfate ions, if they're present, to form a substance of barium sulfate. Now, the importance of this is that this barium sulfate forms a white precipitate. And that would be the observation that we make if we do indeed have sulfate ions present. So a reaction that we could write for this would be Na2SO4 aqueous plus BaNO3 aqueous reacts to make BaSO4 solid plus sodium nitrate, so NaNO3, and we'd need two of those, and they are aqueous. However, you could instead just write Ba2 plus aqueous plus SO4 2 aqueous makes BaSO4 solid. That would work as well. So the next test is going to be for those halide ions. And this can be used to distinguish between the calcium bromide and the ammonium iodide. So we need to remember that the test for halide ions, first you add nitric acid, which of course if this is following the other tests you would have already done, and then you add silver nitrate. So what we would observe, if calcium bromide is present, and therefore there are bromide ions in this solution, is a cream precipitate. Now the equation that would represent this would be an Ag plus aqueous ion would react with the Br minus aqueous ion to form AgBr, which is the solid cream precipitate. So now the last one to look at would be the ammonium iodide. And if that was present and we added this nitric acid and silver nitrate, then we would form a yellow precipitate. Now the equation that's relevant for this is very, very similar. It's just Ag plus aqueous plus I minus aqueous makes AgI solid. And that AgI is the yellow precipitate. So there we have it. We have a lot of possible tests there. We need to be very familiar with all of them, and we also need to make sure that we know the order to carry those tests out. But good work. Let's try the next part now. So now the next part. Two of the substances contained ions of the halogens bromine and iodine. Iodine is used in iodine thiosulfate redox reactions. Cobalt alloys were first used in the Second World War in areas of high temperatures such as plane engines, and is now used for biomedical applications in casting. One cobalt alloy has a required composition of 60% cobalt. A chemist was provided with a sample of cobalt alloy and asked to check its composition met these guidelines. The chemist took 6 grams of the alloy and chlorinated it at 110 degrees. This formed a 100 cm³ solution of cobalt-3 chloride. 10 cm³ of this solution was reacted with an excess of potassium iodide, and the CO3 plus ions reacted with the I minus to form iodine. The liberated iodine was titrated with 1 mole per decimeter cubed of sodium thiosulfate, and the end point was reached at 8.5 centimeters cubed. Here we need to determine if the cobalt alloy met the composition guidelines, and that was 60% cobalt. So first things first here, we need to write some balanced equations. So we know that the cobalt-3 plus ions reacted with the I minus to form iodine. So we know that the I minus is going to get oxidised to make I2. Now if the I minus is oxidised, then that means that the cobalt is going to get reduced. And the cobalt gets reduced here to CO2 plus. As you can see here, I've made sure that this is balanced, not just for the atoms, but also for the charges or the oxidation states. It's very, very important that this is fully balanced because we need this later on in the question when we start doing mole calculations. Now the other reaction we need to write down is one that we do need to have memorised. Is the reaction between the thiosulfate and the iodine. So we need to know 2S2O32- plus I2 goes to 2I minus plus S4O6 2 minus. Obviously you can work this out, but it comes up often enough just to be worthwhile learning that reaction. Okay, so now we've got our balanced equations, we can start to have a look at what we can calculate. And in these titration questions, I always recommend reading them backwards, okay? So the last bit of information that we were told is that we have a 1 mole per decimetre cubed solution of sodium thiosulfate, and we have an end point reached when we add 8.50 centimetre cubed. So we can work out the moles of that thiosulfate by doing 1 times 8.50 over 1,000, which gives me 8.5 times 10 to the minus 3. Now, in this balanced equation, that refers to the 2S2O3, whereas we need to know about the iodine. So that is a 2-to-1 ratio. That means that if I halve the 8.5 times 10 to the minus 3, I'll get the moles of I2. So that gives me 4.25 times 10 to the minus 3 moles of I2. So now we can go forward into the previous balanced equation. We can see that the relationship between I2 and cobalt 3 plus is a 1-to-2 ratio. So now if we want the number of moles of cobalt 3 plus, we need to double the iodine. Essentially we end up back where we started, but this was all important, these steps. So the number of moles of cobalt 3 plus is going to equal 2 times 4.25 times 10 to the minus 3, which of course is 8.5 times 10 to the minus 3. So we've got the number of moles of cobalt now. We know that that relates to 10 centimetre cubed of the solution because we took like a little scoop out of it. We need to know how many moles there were in the original 100 centimetre cubed solution. So in order to do this, we need to times the 8.5 times 10 to the minus 3 that was in 10 centimetre cubed by 10. That gives us 8.5 times 10 to the minus 2 moles of cobalt 3 plus. Now we've got enough information to work out the mass of the cobalt. So we know mass equals Mr. moles, it's MR times by moles. So here we've got 58.9 times by that 8.5 times 10 to the minus 2. Of course, I got the 58.9 from the periodic table. That gives me a mass for cobalt equal to 5.0065 grams. Now, we're trying to compare this to this alloy of 6 grams. So we need to work out what percentage of this 6-gram alloy is cobalt. So we're going to take the mass of cobalt within it and divide it by the mass of the alloy, times it by 100, turn it into a percentage. So here we need to do 5.0065 over 6.0 times by 100, and I get that to be 83%. Now we're asked here, of course, aren't we, to see if this cobalt alloy made the composition guidelines. The guidelines were 60% cobalt. Well, 83% is not 60%, so the answer is no.
Ouch! This is why in some videos I'll explain scratches.